SOE required timed sabotage devices. British planners specified delay fuses. Charges had to explode after withdrawal. Demolition teams needed predictable intervals. Rail lines were preferred delayed targets. Transformers and bridges also required delays. Occupation forces patrolled irregular schedules. Instant fuses reduced escape chances. Mechanical clocks existed for demolition. Those clocks were bulky and conspicuous. They were also expensive precision mechanisms. Supply was limited for field agents. Mechanical timers produced audible ticking. Clockwork risked detection during searches. Clockwork also disliked dirt intrusion. Cold weather affected lubricated gear trains. SOE required something smaller. SOE required something cheaper. SOE required silent timing mechanisms. The answer became chemical delay fuses. The common term became time pencils. The official designation used dry language. The device looked like a short pencil. Length varied with the intended delay range. A typical unit used metal casing. Aluminium or lead alloys were common. One end carried the striker mechanism. The striker compressed a small spring. A retaining wire held the striker. The striker sat above percussion cap. The cap initiated safety fuse cord. The opposite end housed the ampoule. The ampoule was made of glass. It was thin and easily crushed. The ampoule contained corrosive solution. Copper chloride solution was widely used. Other salt formulations were trialled experimentally. The retaining wire passed through solution. The wire material was carefully selected. Steel wire was the common choice. Wire gauge controlled cross-sectional area. A cross-sectional area shaped corrosion time. The agent armed the time pencil. The agent crushed the glass ampoule. They used simple finger pressure. Sometimes pliers were recommended in manuals. Crushing released solution onto the wire. The solution attacked metal surface layers. The wire slowly thinned under corrosion. At some point the wire failed. The spring drove striker into cap. The cap ignited attached safety fuse. Safety fuse length determined further delay. The safety fuse burned at known rate. Approximate rate was a set number. Rates were supplied in training pamphlets. The charge detonated when fuse finished. Overall delay combined chemical and fuse. Chemical delay defined the course timing. Fuse length trimmed final minutes. The system looked simple and elegant. On paper it matched SOE requirements. As small, light, cheap and silent. No moving gears or clock hands. No ticking audible in quiet rooms. Very limited training required for use. Instructions fitted on pocket reference cards. Manufacture sailed easily in dispersed workshops. Components required no strategic materials. No precision machining was strictly essential. Casing could be extruded or drawn. Wire could be standard industrial product. Glass ampoules came from pharmaceutical suppliers. Chemical salts were common laboratory items. The core design encouraged mass production. However, chemistry resisted simple standardization. Real-world conditions complicated corrosion behavior. Laboratory conditions granted predictable timings. Temperature was carefully held constant. Solutions were mixed to precise concentration. Wire batches shared controlled composition. Some test jigs recorded average failure times. Tables were compiled using these results. The tables populated SOE training booklets. Time pencils were stamped with delays. Markings reflected nominal delay at baseline. Baseline temperature was room-like temperature, typically around 20 degrees Celsius. Actual European conditions rarely matched baseline. Agents operated in winter and summer. Devices travelled in unheated transport vehicles. They waited weeks in safe houses. They crossed borders in luggage compartments. They sat inside clothing under stress. They were cached in barns and caves. Every storage condition altered internal temperature. Temperature altered corrosion reaction rates. The corrosive solution obeyed chemical kinetics. Higher temperature accelerated molecular activity. Lower temperature slowed ion movement significantly. A wire dissolution followed Arrhenius-type behavior. Small temperature variations produced large timing changes. SOE chemists understood temperature sensitivity. They ran controlled experiments under varying temperatures. Results showed clear, predictable trend lines. Cold storage slowed delays dramatically. Warm storage shortened delays dangerously, but field temperature profiles were complex. Devices experienced changing conditions over time. They warmed in pockets near skin. They cooled during night outside walls. They sat near stoves during meetings. They rested in damp cellars overnight. Each phase altered overall reaction integration. The agent only saw stamped delay. The stamped number masked accumulated uncertainties. Instructors tried explaining temperature curves. Simplified guidance appeared in training notes. And agents were warned about cold conditions. They were told to expect longer delays. They were warned about hot environments. They were told to expect shorter delays. However, the explanations remained approximate. Field agents lacked thermometers and charts. They estimated conditions by personal sensation. Human perception of temperature is imprecise. Memory further distorted earlier storage history. One time, pencil might stay indoors. Another moved between trains and barns. Both carried identical stamped numbers. Their internal histories differed completely. Their actual delay times diverged widely. Reports from the field reflected divergence. Some charges detonated far too early. Some charges detonated many hours late. Some charges failed to operate entirely. Failure analysis became difficult in wartime, and investigators rarely recovered intact failed units. Explosions destroyed primary forensic evidence. Surviving units were often discarded secretly. Agents lacked safe access to laboratories. They provided narrative accounts by coded messages. Reports mentioned approximate delay deviations. Anecdotes described surprising early detonations. Others described charges firing next morning. Instructors tried collating delay statistics. The dataset remained sparse and skewed. Many operations produced no feedback. Successful demolitions often lacked detailed timings. Time pencils kept being manufactured regardless. Demand remained high for compact fuses. SOE procurement offices pushed large orders. Multiple contractors produced similar subtypes. Quality control varied between production lines. Wire composition varied with steel supplier. And subtle alloy changes influenced corrosion rate. Impurities in copper chloride also mattered. Solution concentration varied between batches. Ampoule volume control was not perfect. Glass wall thickness varied with manufacturer. Breakage force changed accordingly. Partial crushing sometimes left trapped fragments. Trapped fragments limited solution access to wire. Some ampoules fractured only on one side. Solution coverage became uneven across wire length. Pockets of dry surface slowed corrosion locally. This produced irregular thinning of cross-section. Failure occurred at weakest corroded point. Exact position was inherently random. Random position slightly modified timing distribution. Statistical spread increased with manufacturing variation. Engineers attempted to design around variation. One proposal used twin wires in parallel, and another proposal used wrapped filaments bundles. Some prototypes added etched weakness points. Others replaced steel with alternative alloys. Nickel steels were considered for higher stability. Phosphor bronze received limited evaluation trials. Each alternative introduced new uncertainties. Suppliers struggled to guarantee precise wire composition. Metallurgical testing capacity was limited and expensive. Chemists tried adjusting solution concentration upward. Higher concentration restored delays at low temperatures, but higher concentration shortened delays in warmth. The system oscillated between two unsatisfactory extremes. Guidelines eventually preferred conservative delay markings. Units were labelled using cold condition tests. This meant warmer conditions caused early detonation. Early detonation posed higher immediate risk. And charges might explode before agent withdrawal. Agents adopted personal safety workarounds. Some doubled estimated delay before re-entry. Others chose longer nominal pencils for safety. Some limited use to remote targets. Operational directives gradually reflected these habits. Instructors emphasized maximum distance before detonation. Withdrawal routes were carefully pre-planned. Agents were advised against loitering nearby. However, sabotage missions sometimes required observation. Railway attacks needed confirmation of damage. Urban power targets required visual verification. Operators balanced risk against intelligence value. Unexpected timing undermined that calculation. A charge intended for night detonation instead fired during busy evening traffic. An intended dawn explosion occurred mid-afternoon. And such deviations altered civilian exposure patterns. They complicated political risk assessments in London. Committees discussed acceptable civilian risk boundaries. Time pencil behaviour entered those discussions. Some officials distrusted chemical delay devices. Others accepted their unpredictability as wartime cost. The debate influenced procurement orders temporarily. Alternative timing systems received renewed attention. Electrical delay systems were examined again. Battery-powered detonators offered fixed circuits, but batteries degraded in cold and damp. Electrical circuits required additional training. Spare parts increased load on supply chains. Mechanical alarm clock fuses remained options, they stayed noisy and bulky in practice. Time pencils remained the default compromise, their advantages aligned with covert operations. They were easy to conceal in clothing. They resembled ordinary stationery items. Custom pockets held several units discreetly. They could be posted in packages. Inspectors overlooked small cylindrical objects often. Ammunition belts could hide them effectively. Explosive charges accommodated them without redesign. Plastic explosive blocks incorporated pencil recesses. Trainers taught simple assembly procedures: fit fuse into detonator pocket, secure with binding tape if needed, do not crush ampoule prematurely, crush only at final arming moment, avoid rough handling after ampoule crushing, keep fuse oriented appropriately if instructed, attach and route safety fuse carefully, avoid sharp bends in safety fuse, check fuse for visible damage points, confirm required approximate delay before commitment, and note temperature and conditions mentally. Add personal margin for uncertainty allowance. Many of these steps relied on judgment. Judgment varied widely between operators. Some operators were former engineers. Others had agricultural backgrounds exclusively. Training duration could not equalize all differences. Course materials simplified chemical explanations greatly. Presentations focused on operational convenience. The phrase reliable within limits appeared frequently. Reliability remained linked to environmental control realism. Laboratory tables showed nominal delay ranges. These tables allowed plus or minus tolerance. Tolerances widened at lower temperatures significantly. Printed examples used stylized winter scenarios. They rarely addressed rapid temperature cycling. In the field, cycling occurred repeatedly. Devices moved indoors and outdoors regularly. Surface temperature lagged behind ambient changes. Internal solution remained cooler than exterior initially. Thermal gradients developed within pencil casing. Gradients affected corrosion at different wire segments. No agent could calculate such gradients directly. Designers accepted this as irreducible complexity. They still searched incremental improvements. One modification introduced insulating sleeves externally. Sleeves reduced rapid cooling after body contact. Another modification specified darker casing finishes. Darker finishes absorbed sunlight more effectively. This could warm devices in cold sunlight. However, it also heated them in shade. Shading patterns around bridges were unpredictable. Sun angle changed seasonally and daily. These effects remained second-order influences. Water immersion posed additional complications. Some charges sat under water lines. Canal demolitions and harbour work required immersion. Water temperature remained low and stable. Cold water prolonged delays dramatically. Few standard tables covered submerged conditions. Agents improvised timing expectations from general warnings. Occasional post-war tests revisited immersion behaviour. Results confirmed extreme delay lengthening. Some fuses took far beyond nominal times. Others failed to break wire at all. Corrosive products formed protective layers locally. These layers inhibited further dissolution progression. Stagnant water reduced oxygen availability. Redox behavior shifted under limited oxygen. Design assumptions from aerated tests no longer held. Manufacturing records rarely noted immersion exposures. Quality control largely ignored such niche conditions. Prototype evaluation had been narrower originally. Initial tests were brief and controlled. Sample size remained limited for resource reasons. Early field trials appeared acceptable in reports. Operational urgency accelerated adoption after trials. Lessons from later missions arrived too slowly. Production capacity was already committed by then. Changing design mid-war carried disruption risk. Stockpiles already existed in forward depots. Scrapping inventory would waste scarce effort. Command organizations therefore tolerated time pencils' imperfections. They issued warning notes instead of cancellations. Circulars reminded users about strong temperature effects. Some versions added colored coding bands. Colors indicated approximate calibration climate assumptions. The units intended for colder regions used a one band. Units intended for temperate use used another. This system remained informally documented in places. Field agents rarely received uniform coded sets. Logistics chains mixed batches in transit. Resistance groups shared consignments across regions. Pallet labels lost meaning during redistribution. time pencils of different pedigrees intermingled. Predictability decreased for theirs under such mixing. SOE chemists continued refining formulations. They analyzed corrosion products microscopically. They adjusted pH to optimize attack rate. Buffers were introduced to stabilize solution over time. Contaminant limits were specified for suppliers. Analytical methods checked incoming chemical batches. Colorimetric tests screened copper concentration rapidly. The specific gravity measurements identified gross mixing errors. Ampoule filling machines were recalibrated periodically. Operators received stricter instructions on fill volumes. Spot checks weighed random production samples. Still variability persisted at the wire interface. Surface condition affected corrosion initiation greatly. Drawing processes left residual stresses. Residual stresses influenced crack propagation speed. Minor surface scratches served as initiation sites. Packaging and handling created those scratches sometimes. Manufacturers tried polishing wire before assembly. Polishing changed surface chemistry in other ways. Protective films formed on the polished surfaces. Films slowed initial attack until removed. The first minutes after crushing became complex. Solution had to penetrate and dissolve films. And then active corrosion proceeded at expected rate. Any variation during the early phase changed total time. Standard specification sheets struggled capturing early dynamics. Therefore, tables represented statistical averages only. Individual units could deviate significantly from tables. Field instructions repeatedly stressed this limitation. Instructors described published numbers as guides. They discouraged exact planning around single minutes. Despite guidance, operational planning still used numbers. Rail disruption required coordination with train timetables. Saboteurs selected nominal delays matching scheduled gaps. They wanted explosions between specific train movements. Deviation changed which train encountered damage. Sometimes that produced reduced effects on traffic. Sometimes it increased disruption unintentionally. Yet in urban settings, timing affected blackout patterns. Cutting power during daylight had limited immediate effect. Cutting power during night changed civilian routines. Time pencil unpredictability blurred these distinctions. London staff recognized this planning handicap, but alternative tools carried own disadvantages. Chemical delays remained easiest instruments to supply. They did not require captive screws or holders. They did not require winding mechanisms before use. They tolerated moderate rough handling before arming. They operated without external power sources. Careful users could mitigate portion of risk. Experienced agents developed personal empirical adjustments. They mentally corrected nominal numbers by season. They recalled previous missions' delay behavior. They remembered local climate characteristics by region. This experiential knowledge rarely reached formal doctrine. Transmission of such nuance relied on debrief meetings. Many agents never returned for debriefing. Operational attrition removed significant user expose. Training schools did conduct post-war experiments. They recreated approximate wartime storage patterns. Devices were cycled through temperature regimes. Tests measured distributions of actual delay times. Histograms showed broad unpredictable spreads. In some scenarios, range covered multiple hours. In warmer regimes, spread compressed but shifted earlier. Investigation teams drafted lengthy technical memoranda. They recommended restricting use in specific climates. They proposed new scales printed on casings. Scales would show temperature-dependent delay bands. Implementation required redesigned casings and stamps. And by that time, demand was already declining. Conventional armies were advancing across continents. Reliance on clandestine sabotage slowly decreased. Stockpiles of time pencils still existed, though. Certain units used them during formal demolitions. Army engineers appreciated compactness for small tasks. Bridges and culverts still needed timed demolition. Even regular units experienced temperature variations. Cold alpine operations demonstrated worst-case behaviors. Mountain demolitions reported extreme delay extensions. Officers reverted to mechanical clocks where available. Post-war analysis meetings reviewed all timing devices. Committees compared chemical, mechanical, and electrical systems. They ranked devices by predictability and robustness. Time pencils scored well on simplicity and size. Then they scored poorly on environmental stability metrics. Some nations retired them from standard inventories. Others retained them in reduced roles. Technical reports circulated within Allied ordnance establishments. They used neutral language describing corrosion delays. They catalogued each variable influencing performance. Wire diameter, solution strength, and temperature dominated. Storage history and mechanical damage followed closely. Operator training emerged as probabilistic factor. No single modification removed underlying sensitivity. Later designs explored alternative chemical mechanisms. Some used expansion of swelling materials, others used slow dissolution of plug components. None fully escaped basic temperature dependence. Modern equivalents often incorporate electronic timing. They use microcontrollers and quartz oscillators. Hence, they rely on battery chemistries with decompensation. Software applies correction factors based on measurements. During the war, such sophistication was impossible. Resources and time were sharply limited. Under those constraints, the time pencil persisted. It served as workable compromise for sabotage. Its reputation among users remained mixed. Some praised its convenience repeatedly in reports. Others viewed it as unpredictable liability. The historical record preserves both viewpoints. Operational files mention irregular detonation intervals. Design files describe repeated attempts at improvement. Neither set fully resolves uncertainty question. Temperature remained hidden adversary throughout deployments. Every crushed ampoule began silent chemical countdown. The countdown obeyed reaction rate laws. And those laws answered primarily to temperature. Field conditions rarely matched clean laboratory assumptions. Real bridges, real trains, and real winters intervened. The explosive briefcase waited against its target. Inside its casing, the pencil continued corroding wire. Agents moved away using planned escape routes. Some were already far across borders. Some still heard delayed explosions behind them. A small device tried to define time precisely. The surrounding environment kept redefining it instead.